Yeah, where you would have heard of two-phase flow. So what is a two-phase flow? Is like both gas, oil flowing together. So now here it can also be a three-phase also. Like you can have a gas phase, oil phase, and water phase flowing together. So when you have so two phase here is vapor phase and liquid phase. So inside liquid there can be oil, water, etc. So when you have a two-phase flow, then based on your amount of gas and amount of liquid present, you will have different flow regimes. So these are the different flow regimes. So if you look at the first is the bubble flow, the second one is the slug flow. Here it is the churn flow, and in churn flow there are two different types, and then your annular flow and mist flow. So what are the differences here? So as I said, when you're in case of gas, so your density is going to change because of the pressure drop. But in case of two-phase, you still have a complication. What happens is when your pressure or the temperature changes, your phase also changes in the two-phase region. So some portion of oil gets flashed into vapor because your pressure has reduced now. So when there is going to when flashing is going to happen, your vapor fraction at each length of your pipeline is going to keep changing. So when there is change in your vapor availability, then your flow regime also can change because of the velocity. So now let me explain in detail what is a bubble flow. So when you have a very high velocity of gas, what it does is it bubbles out all the liquids, and all the liquid phase will remain in bubbles. So you have a bulk gas phase region, and then you have liquid bubbles in between. So this flows in the pipeline. So this is the bubble flow. When it comes to slug flow, you have gas zone, and then you have a bulk of liquid zone, and again a gas zone, and then a bulk of liquid zone. So this slug flow should generally be avoided, because in the operations what happens is you get bullets of liquid coming out frequently, so that will affect your steady operating of the plant. So that's the reason you should generally be avoiding slug flow. Slug flow happens when your gas flow rates are very less and your gas velocities are very less. So it will not be able to push the liquid. So it allows the liquid to accumulate. So because of this accumulation, your upstream pressure will start increasing. And once it reaches the pressure, it could push the liquid out, then it pushes that slug, and then again next it starts accumulating. So that's why this junk of liquids keeps generating and a gas phase. So here your gas gets accumulated, and once the upstream pressure increases, it pushes this bullet out. So that's the slug flow. And in churn flow, so here it's also similar to slug flow. You have a bulk of liquids, but then your gas is not going to stop until it accumulates the liquid. Gas also keeps flowing. Some gas keeps flowing to the sides, and then the liquid accumulates and it pushes out the liquid. So this type of flow is also to be avoided. And here annular, so this churn flow 1 and 2 are different location of those liquids. So that's similar flow regime. And then when you come to the annular flow, what happens is when you have a very high velocity of gas, the liquid forms the film at the sides of the tube, and the gas will flow between the liquid region. So this is the annular flow. So here also you have a liquid film at the sides of the tube, and you have a high velocity gas which is going to pass in between. So this regime is also to be avoided. And then the next is mist flow. When you still have higher velocity of gas, it bubbles the entire liquid into form of small mist like particles. So the difference in bubbles is the particle sizes are bigger here. In the mist flow, the particles of liquids are very small. So that's the different flow regime. So what happens in the multi-phase flow is when your pressure and temperature changes across the length of the pipeline, your flow regime also changes. And when the flow regime changes, your equations which are used for this flow regime is different as compared to the equation which are going to be used for this regime. So that's why the proper, in this case, the simulation will split into number of small sections, so that at each section it will determine the type of flow, and according to the type of flow it will select the appropriate equations which are supposed to be used for that particular flow region. So you will have an accurate pressure calculations. So next, so that's the, as I said, there are different flow models which are going to be used. So these are the different models which are available. So when you have horizontal flow, vertical flow, and when you have liquid hold up, so these are the different equations which are available. So based on these equations, you will have, so these equations are already modeled in the simulations also. Like if you look at Hysys, then you have all of these equations available. So when you have a two-phase regime, it automatically picks up the appropriate equation and it solves. So each equation has got some limitation. So this equation cannot be used, or it will not predict accurately when there is a horizontal flow. And then when you use Dill and Thomas, so you can use it for vertical flow, but for liquid hold up or flow map, that is, it will not predict the flow regimes, and it will not change the equation according to the flow regime. So this flow map is actually determining your flow regimes, and then liquid hold up is also determining the slugs, whether there is any formation of slugs or not. So that is about different equations for pressure drop calculations, or for the hydraulics. So now let's move on to the next. So the other requirement for the simulation is, when you have a typical network like this, so this is a typical Firewater network which will be available. So here your pumps are located at this location, and then you have a pipe which is coming out from discharge. So this is the tank which is going to store your Firewater, and you have a suction lines, and then each pump has got individual section, and then the discharge here. So the discharge line, this is the discharge header. So here is the deluge valve, what they call. So whenever there is fire, this valve opens, and when there is a decrease in pressure here, the pump automatically starts and it starts feeding your Firewater network. So what happens here is, so now the let us look at the furthest location. So this nozzle. So when you have the water to be delivered to this nozzle, so in that case, say this pump is discharging, so the liquid from here has to travel along this, and then it goes like this, and then it has to travel along the header, and then the subheader, and then through the lateral, and it has to reach this point. So now this liquid has suffered the maximum pressure drop because it has traveled the furthest point. But when you look at this nozzle, so say let us look at this nozzle. So here the distance is very less because it is the first nozzle which is going to come here. So when the pump starts pumping, so this will have a higher flow rate because this has got higher pressure at the inlet. So when it has higher inlet, so higher pressure, so there is a large pressure difference across this point. So there will be huge flow rate which is going to flow across. Sorry, even compared to this, you will have this nozzle because it is still at the lower point. So this nozzle will have a higher pressure. So here you will have higher flow rates at this nozzle because this is the first nozzle. But when you look at this, it will have little higher flow rate, but this will have the lowest flow rate. So what you have to do is you have to solve for each of these points. So you should also meet the required flow rate at the furthest nozzle also. So you should be able to calculate the entire system flow rate. So here, when say your flow is only happening till this point, then the pressure at this point will be different. But when your flow is happening up till this point, then your pressure at this point will also be different. So when you have to do a network analysis, so in that case also simulation is required. So when you have such networks, you will calculate the hydraulics at each location, and by solving the equations, you can determine the pressure at each point. So based on that pressure, you can also calculate the flow rate at the each nozzle. So what generally happens is these nozzles will have higher flow rates, but these nozzles will have lower flow rates because it has suffered the longest hydraulic path. So this will have the lower inlet pressures. So this will have the lower flow rate. So based on your required flow rates, you should be able to meet the required flow rate even at this location. So accordingly, you should develop the pressure from the pump, and accordingly, you should also meet the flow rate. So for that, hydraulic network also simulation will be helpful. So you can, if you have to solve manually, then you will solve the manual way to determine what is the pressure here. But then when a flow starts happening, there will also be flow rate. If you say you are going to calculate manually the pressure drop up to this point, so you will calculate the pressure at this location and it will calculate the flow rate. But actually what happens is when the entire flow flows, there will also be flow rate which is going to go out through these nozzles. So when there is going to be flow out, so there will be difference in flow rate at each of this location and then at each of this location until this point. So that flow rate, again, it changes based on the pressure drop. So it will be solving iteratively. So it takes longer time when you do it manually. So that's why simulation will help you to solve those iterative calculations and calculate your required flow rate. Yeah, so now let's move on to the next. Okay, so in simulation, what are all the advantages, what are all the other other advantages that you're going to get? So here in component selection, all simulation database, you will have all set of components available in the database. So you can directly use those components. Or if you have your molecular weight and density value for each of your component, like if you know the structure of that component, then you can determine the molecular weight. And then if you know the density of that component, then you can also create a hypo component. What is hypo component? Is generating a component which will behave in similar way as that of your component what you're having. Say you have a mixture of components, say like in petrol or diesel. So it has a mixture of different hydrocarbons which are available. But as a bulk of the liquid, you can determine the density and you can determine the other parameters. So based on those boiling point and density, so when you feed in those parameters into the Hysys, it will develop a hypo component. So what is hypo component? Is that it will behave in similar way as that of the mixture of liquids what you have. So that advantage you have in simulation. And then you also based on assay data. So what is assay data is there are different testing methods like ASTM D86 or ASTM D1186. So different testing methods. What you do there is you take a bulk of liquid, you take a different volume, like say 100 ml of your liquid, and then you start heating that liquid. So the vapor keeps coming out of the liquid. So you condense those vapors and you calculate the percentage of liquid which are getting vaporized. So say 5% is vaporized, at what temperature you will note down, and then at what temperature 10% of your liquid, like 10 ml has got vaporized, so you will note down at that temperature. So similar, so in that way you will generate a table with the boiling point at one and then the percentage vaporized at other column. So when you have such data, you can also feed those data. So that is based on specific testing methods, like ASTM D86 is for your atmospheric distillation, and then you have ASTM D1186 for vacuum distillation. So different testing methods. So using those testing methods, you can determine the percentage vaporized, and using that value, you can generate hypo components, set of hypo components in the simulation. So that will represent your oil. So here in that case, you will what it does is it develops different boiling hypo components. Like it will name it as NBP 50. So that will have set of components which are going to boil at 50 degrees Celsius or something. So in that way, you can generate hypo components, which is hypothetical component, which is not existing in reality, but it will have a behavior similar to your component, which is a mixture of components. So that's the other use of so this is what the different testing methods, as I've said: true boiling point estimation, ASTM-D86, ASTM-D1160, etc. So based on that testing methods, you can generate the hypo components for your use. And then next, the important thing that you have to look in flow is here you have to select the appropriate fluid package for your use, because the fluid package is important while using the simulation. So when you select a wrong fluid package, each of that fluid each of the fluid package will have a different set of vapor liquid equilibrium data, so which we call it as VLE data. So when you use the so as I've said in the earlier slides, like if you have to see how much is your liquid content or how much is your vapor content in the pipe, so that is all dependent on your vapor liquid equilibrium data, which is VLE data. So that VLE data is specific for each of the property package. So that property package will have will be suitable only for those set of components which are designed specifically for that fluid packages. Say if you have a Peng Robinson, so here PR stands for Peng Robinson, then SOAR Peng Robinson, and then this is so these are the different fluid packages which are available in the simulations. So this here I have given different type of systems for which the appropriate fluid packages can be used. So this is just a general guideline, but you will have to be more specific when you are selecting the fluid package. Say when you have a glycol system, then in that case when you select, so some of the simulations itself will give you warning when you select the wrong property package with the wrong selected component. So that selecting proper fluid packages are very important. Only then you will have the accurate prediction of your vapor liquid fraction distribution. Yeah. So now let's move on to the next. So here, what are the minimum parameters required to completely define a stream? So if you look at any simulation for the stream to generate all the properties like viscosity, density, molecular weight, different properties will be available from the simulation. So for that, to get all those simulations, you would require minimum parameters that are to be defined. So what are all the minimum parameters that you would require to define the stream? Yeah, so here that will be dependent on your degrees of freedom. So you would have all learned during your college for your about degrees of freedom. So degrees of freedom should be satisfied for the entire system. Degrees of freedom is indirectly, so say you're going to solve the set of equations. So for solving those set of equations, you would require all the required values which are to be available. So if you have x, y, z, then you should need 3 equations. So only then you can solve those 3 equations. So like that, you will be able to meet the degrees of freedom. Only then the equations can be solved. Otherwise, the equation will not be able to solve. So then it will show, it will not be converged in your simulation. So here, when you have a stream, so VF is vapor fraction, pressure, and temperature. So out of these 3, you would have to specify any 2. So either vapor fraction and pressure can be specified, so that Hysys will automatically give you the temperature, or if you specify pressure and temperature, it will give you the vapor fraction. So you should use any of these, any 2 out of these 3, and then you should specify your composition and flow rate. So if you give all of so here You need to specify 2 and then these 2, so your degrees of freedom will be satisfied. So once you give those, then the stream will get converged. Yeah, so now this is a typical phase diagram. So this here, this is the phase diagram, what is there. So this phase diagram is what I was explaining. So this will be dependent upon your fluid package selection. So only based on this phase diagram. So here if you will see, beyond this it will be in liquid phase. When this is your pressure and temperature zone. So when your temperature and pressure are lying in between these two lines, then it will exist in two phase conditions. And when it goes beyond this line, it exists in the vapor phase. So all of this phase diagram you would have you would have learned during your college. So here this is the critical point. So at this point it will be existing all phases will coexist. So you cannot sharply differentiate whether it's a liquid phase or a vapor phase. So here when you see this will be your boiling zone, so bubble boiling point line, and this will be your dew point line. So when you are going to increase your pressure, so here when your pressure and temperatures are in this region, then it is at the saturated conditions. And when you further increase pressure or when you further increase temperature, it will start. So this is the liquid zone, which is at the saturated conditions. So when you increase your temperature, it comes into this zone. So when it enters into this zone, it will start vaporizing. So it will start existing in the two phase. So this line, the points across this line will be at the saturated conditions. And when you go into this zone, it will become a two phase regime. And when it comes to this zone, it is at the saturated vapor conditions. So when you go beyond this line, it will exist in the vapor phase, or it is in the completely gas phase. So until this line, it will be in the two phase zone, and exactly at this it will be at saturated vapor conditions, and when you further increase, it becomes the gas phase. So this is the phase envelope. So this type of phase envelope can be developed in any of the simulations. So like this is the snapshot which is from the Hysys. So for each of the component system what you have, you can develop the phase envelope. So using phase envelope, you can determine your boiling point of those components, and then boiling point curve, dew point curve, and then this is the critical point what it has specified. So say in this, if your operating pressure is 200 psig and your temperature is -100, then you are in the two phase regime. Say if your operating pressure is 600 psig and your temperature is -200, you are in the liquid zone. So it is the subcooled liquid. So until this point also it is subcooled liquid. This square what you see is all the saturated liquids, and all this triangle are the saturated vapor points. So when you go beyond into this region, say your operating temperature is 100 degree F and maybe 200 psig, then you are in the vapor zone. So that is the reading this phase envelope. So all of this phase envelope will depend upon your property package also. So you would have all done flash calculations. So what is flash calculation? The bubble point curve and dew point curve for the mixture of components can be generated using the envelope utility option. Bubble point temperature of the stream can also, in high simulations, you can also determine what will be the boiling point of your mixture of components. So if you want to determine your boiling point, you can specify your pressure and you can specify the vapor fraction as 0. Then you will have the temperature calculated, and that temperature will correspond to the boiling temperature of that fluid. And then next, dew point temperature, like you can also calculate the condensing temperature or the dew point temperature. So you can specify the pressure and you can specify vapor fraction as 1. By doing so, you will get the temperature calculated in the stream. So that temperature will correspond to your dew point. So any reduction in temperature beyond that point, it will start forming liquid, and any increase in temperature beyond that point, it will be in completely vapor zone. So that is the dew point temperature. So you can also calculate the bubble, earlier you have calculated the boiling temperature. You can also calculate your boiling pressure by specifying temperature and vapor fraction as 0. The calculated pressure will correspond to the boiling pressure. So indirectly what you can do is you will be determining each of this square. So each of that point will correspond to the boiling conditions at that specific temperature or pressure. So say if you specify your temperature as minus 150 degree F and vapor fraction as 0, then the simulation will predict the boiling pressure as 200 psig. If you specify 200 psig and give your boiling point as vapor fraction as 0, then the simulation will predict the for 200 it will predict in the range of minus 170 degrees F as the boiling point. So that is what this envelope is going to be used for. And then specifying pressure and temperature of the stream, vapor fraction of the stream can be obtained. So if you specify say minus 50 degree F and 200 psig, then you will know what is the vapor fraction. And so 1 minus that vapor fraction will give you how much is your liquid available at that condition. So that is what is specified here. Next usage is for generating stream properties. So when you have mixture of components, say number of components are there, then the combined density. So when you have pure components, it is easier to get the database to have the density values. But when you have mixture of components, knowing their mixture density and then critical properties, etc., can be determined using the simulation. So liquid flow at standard conditions, gas to oil ratio, mass heat of vaporization, which is latent heat, enthalpy of stream, Cp by Cv of stream, all of this can be developed when you have the simulation. So what are all the significance of each of these properties? So as I said, in case of compressible fluids, your volumetric rate is going to change at each temperature and pressure. So what generally is followed in industry is they specify the gas flow rates at standard conditions. The standard condition is 60 degree F and atmospheric pressure. So at that condition, you will have the volumetric rate. So that is a specified value because the conditions are also fixed. But when your temperature and pressure changes, your volumetric rate will change accordingly. So in actual, based on your actual conditions, using the standard gas flow rate, you can determine what is the actual flow rate at that particular temperature and pressure. So because if you have to specify actual conditions, then in the entire plant you will have different operating zone. So say if you have your operating pressure varies from 20 bar to down to 5 bar, then you have set of huge range. So in that range, specifying flow rates at each location will not be possible. So only for that, for simplification, it's generally specified at the standard conditions. Then using that standard condition flow rate, you can calculate the actual flow rates at different points. So for that, developing those standard gas flow based, if you have your actual flow rates, you can also determine the flow rate at standard conditions. So for all of those values, simulations can be used. And then you have different miscellaneous unit operations like a conversion of volumetric. So if you have your mass flow rate available, then you can use the adjuster operation and then you can determine your volumetric rate. And then as I've said, if you have your standard volumetric flow rate, you can determine your volumetric flow rate at different operating conditions. And then you can use set, balance and spreadsheets if you want to do certain small calculations before feeding the parameter for the next unit operation. Say like the pressure drop for that specific unit operation is going to be some 30 psig. Then if you want to just subtract 30 psig from your inlet pressure and use it as the input for the next unit operation, so that can be done. You can just use the spreadsheet. You can input the value like you can the simulation automatically can pick the value from the outlet of a stream, and then it can subtract the 20 psig or 30 psig pressure drop which is going to happen across that unit operation, and then you can add that, use that value as your input for the next unit operation. So that is also possible. So you can perform small calculation in spreadsheet, and then you can pass on the result for as the input to the next unit operation. And then if you look at distillation, then in the distillation you would have all seen the TXY, PXY plot. So those plots can also be generated. So using that plot is important to determine whether there is any azeotropic formation or not. So only when you have an idea of the azeotropic formation, you can design the system suitable for that separation. If you have to separate those components out, then you should select appropriate system. So when you know the details of the TXY PXY plot, you will be able to determine whether azeotropic distillation is required or a binary distillation can be sufficient. Or if you have multi components, then you can look at different different flow sheet possibilities, and then you can arrive at which is the optimal way to do it. So this is a typical XY plot. So when there is so this is the horizontal line. If the distance between the horizontal line and the blue line is more, then the separation is easier. If it is very close, then you would require more number of stages to separate the components. So this is a binary plot. So here you will have the so this is the separation and efficiency. So if you have more difference between the red line and the blue line, then the separation is easier. If it is very close, then you would require more number of stages to split out. So whenever, so this is since this blue line is not crossing the red line at any of the point, there is no azeotropic formation. So you can determine whether azeotrope is going to form or not using this plot. And whenever there is azeotropic formation, it will cross. So I will show an example. So here, if you look at this plot, there is a crossing. So you cannot purely split 100% or 90%, 99% split of those components, because it's going to form an azeotrope. So whenever there is azeotrope formation, you will have to go for azeotropic distillation. You have to introduce a third component which will break the azeotrope, and then you will have to separate those three components out individually. Or you can go with extractive distillation or other methods, so that you can split these components into pure components. So that is so you can use this plot to determine whether there is any azeotropic formation or not. So once you know that there is no azeotropic formation, then you can use a shortcut column in the simulation, and you can determine the minimum number of trays required, what will be the optimum feed inlet stage, and then you can know the reboiler duty, condenser duty. All those preliminary values can be obtained using a shortcut column. But you cannot simply go and start with the shortcut column, because your shortcut column will not predict whether there is any azeotropic formation is going to happen or not. So for you to know whether your component system is going to form azeotropes or not, you should first plot this XY and PXY, TXY plot, look at those plot, and then only you can decide whether there is any azeotropic formation or not. Based on the TXY plot, you can determine whether it is a minimum boiling azeotrope or a maximum boiling azeotrope. What is minimum boiling azeotrope or maximum boiling azeotrope? So each of that azeotrope will have a different boiling point. So you have two components. If your azeotrope boiling point is higher than the boiling point of these two individual components, then that is the maximum boiling azeotrope. And in case your boiling point of that azeotrope is lower than the boiling point of the two components, then that is the minimum boiling azeotrope. So based on that, you can determine what type of azeotrope is going to be formed. So to have all those idea, you should have always first when you are going to start the distillation, it is first step is to plot the TXY PXY plot, and then only then you will know the behavior of that components. So based on that, in the next step, using shortcut column, you can have an idea of the number of stages. So what a shortcut column does is, you would have all read about Fensky-Underwood equation during your college days. So it would give you the so based on the light key component and heavy key component, it will specify the minimum number of stages required, and it will also tell you an idea of reboiler duty and condenser duty required for that particular split. So that's with the plot, TXY and PXY plot. And then next, let us move on. So we are moving towards the end of the presentation. So what simulation does is it converges at different point, but then whether it is a realistic convergence or not, you should be able to judge. So that's what I was saying. If you straight away go and use a shortcut column, so if there is any azeotropic formation for that set of components what you have selected, so shortcut column will not determine, will not give you a warning that it is going to form azeotrope. Simply it will give you the number of stages required, and it will also specify the reboiler duty and condenser duty required. And if you're going to develop a distillation column based on that result, you will not be able to separate, because there is a azeotrope formation. So it is your responsibility to first check the XY plot and then see whether any azeotrope is going to form or not, and only based on that you can determine the number of stages. So always your judgment and your values are important, because you cannot blindly go with the simulation results. You should be able to, so your inlet, your procedure should be correct, and your values are also should be correct. Other problem is also, you should be like I have explained in the earlier slides, selecting proper thermodynamic package. So what happens is, some thermodynamic packages, if you choose the wrong thermodynamic package, then it will also not predict the azeotropic formation. So even in that case, if you select a wrong thermodynamic package and plot the XY plot, so you will not see any azeotropic formation. But then in reality, if that thermodynamic package selection was wrong, then there will be azeotropic formation, and again you will be ending up with wrong results. So in all of this, you should be taking care when you select the simulation property package.